Quantum Internet Breakthrough. Connecting computers across vast distances, quantum internet breakthrough. Connecting computers across vast distances, a recent advancement in quantum technology, could pave the way for a global-scale quantum internet, significantly expanding the range at which quantum computers can communicate with each other. Previously limited by distance, quantum computers could soon connect across continents thanks to a new method of building key components. The distance barrier in quantum communication. Quantum computers possess remarkable processing capabilities and speed, but effectively utilizing this power requires a robust and interconnected network. Currently, a significant hurdle is the difficulty of linking these computers over long distances. The maximum distance for communication through fiber optic cable was previously restricted to just a few kilometers. To illustrate, even with fiber cables connecting them, a quantum computer at the University of Chicago's South Side campus couldn't establish a connection with one located in downtown Chicago's Willis Tower. A 200x increase in connection range, research published today in Nature Communications by Assistant Professor Tian Zhang at the University of Chicago Pritzker School of Molecular Engineering, UChicago PME, proposes a solution to this limitation. Zhang's method theoretically extends the maximum connection distance to an astounding 2,000 kilometers, 1,243 miles. This change means that the same UChicago quantum computer previously unable to reach the Willis Tower could now connect and communicate with a counterpart in Salt Lake City, Utah. For the first time, the technology for building a global-scale quantum internet is within reach, said Zhang, who was recently awarded the prestigious Sturge Prize for his work. The science behind the breakthrough linking quantum computers involves establishing quantum entanglement between atoms transmitted through a fiber cable. The longer these entangled atoms maintain quantum coherence, essentially, their ability to hold a quantum state, the greater the distance between computers that can be linked. Zhang and his team significantly enhanced quantum coherence times by improving the fabrication of erbium atoms, a crucial element in creating entanglement. They increased coherence times from 0.1 milliseconds to over 10 milliseconds, with one instance reaching 24 milliseconds. This improvement would theoretically allow quantum computers to connect across distances of 4,000 kilometers, roughly the distance from UChicago PME to Wakania, Colombia. Not new materials, but a new method. The innovation wasn't about new materials, but rather how those materials are constructed. Researchers utilized a technique called molecular beam epitaxy, MBE, instead of the traditional Czochralski method to create the rare earth doped crystals required for quantum entanglement. The Czochralski method, Zhang explained, is like a melting pot where ingredients are mixed and melted at extremely high temperatures, over 2,000 degrees Celsius, before slowly cooling to form a crystal. These crystals are then chemically carved into computer components. In contrast, MBE is more akin to 3D printing, building the crystal layer by layer. "We start with nothing and then assemble this device atom by atom," Zhang said. The quality or purity of this material is so high that the quantum coherence properties of these atoms become superb. Adapting existing techniques, while MBE is a known technique, it had never been applied to create this specific type of rare earth doped material. Zhang and his team collaborated with Assistant Professor Xiulong Yang at UChicago PME, an expert in materials synthesis, to adapt MBE for this purpose. Expert validation, the advancement has garnered praise from leading experts in the field. The approach demonstrated in this paper is highly innovative, stated Professor Dr. Hugues de Riedmitten from the Institute of Photonic Sciences. It shows that a bottom-up, well-controlled nanofabrication approach can lead to the realization of single rare earth ion qubits with excellent optical and spin coherence properties. What's next? Zhang and his team are now focusing on testing whether the extended coherence times enable actual long-distance quantum connections. Their next step involves linking two qubits, each housed in separate dilution refrigerators within Zhang's lab through 1,000 kilometers of spooled cable. This initial test, while not the final step, will prove crucial in validating the technology and bringing the vision of a global quantum internet closer to reality. This breakthrough represents a significant step towards a future where quantum computers can be seamlessly interconnected, unlocking unprecedented computational power and driving innovation across numerous fields.